Good morning. All right, so we've got our first quiz on Friday. It was going to be all of chapter 1, but I really don't think we're going to get to section 1.5 today, so I'm just going to go till 1.4 for the quiz. So don't worry, I'll readjust the schedule. It's fine, but 1.5 is really big, so I didn't want to push it. All right, so kind of to get us all set up for the quiz. So for the quizzes and tests and well, that's it, but quizzes and tests, you'll have to submit your work so that I can mark your work as well. For the quizzes, I won't mark it, I'll just look at it. But you have to submit it so that I have a record of everything you've done. So, because the quizzes, I think we're having, I want to say, we're going to do 7 quizzes. So that's a lot of quizzes. And they're worth a total of 15%. Right, so roughly, 2% each. So that's why I'm not gonna mark that work. It'll just be from your Webassign grade, but I still need to see your work, right? Make sure, because if you don't submit any work, then I'll take away your grade. So you want to submit your work. How we're gonna do that is using Gradescope. I don't know if you guys have used Gradescope before. Cool. One thing I learned the hard way is that there's gradescope.com and gradescope.ca. Initially, I was using .com, but now I'm moving over to .ca. So if you have a .com account, then you'll have to create a .ca account. Okay, so quiz number 1 on Friday. Okay, and it'll be on sections 1.1 to 1.4, right? Up to kind of the end of today, or definitely up to the end of today. I don't know how far we'll get into 1.4 either, so.
Just to kind of, for Gradescope, and I might have blanked on if we were doing CA or .com.
We're doing .ca.
.ca, okay. I assume that we're going to be getting a code to add the course. Okay.
Way ahead of me. So maybe I just need to write faster. So we've got our quiz, and you will need to submit your work to gradescope.ca, right? And I'll just kind of highlight here so you don't go to the wrong side. So in our course, I think is it called a course number? Let me go there. Okay, so if I go to gradescope.ca, okay, then I want to sign up. Let's go as a student, and your course entry code, that's what it's called, okay? Course entry code is 9, capital X, capital E, capital Z, capital N, capital M. I'm trying to think of what the, what's it called, that shorthand? 9, xylophone, echo, zebra. Nicholas Michael? No, I think that's fake. Anyways, so that's your course entry code. And what I did was, just in case you haven't used Gradescope before, just to get some practice, I posted a diagnostic test on a Webassign. So how it's going to go is you're going to get your questions from Webassign still, and then you're going to do your work on paper or a tablet. If you have a tablet, then you kind of bypass the scanning element. But if you're just working on paper, then that works too. So then you do your work on paper. Make sure you label all the question numbers very clearly, because that way you'll be able to tell me where the questions are. I think you'll find that it's easiest if you just use 1 page per question. I know that feels like a waste of paper and everything like that, but if you just have 1 page per question, or each question on a new page, I should say, in case your question exceeds a page. But anyways, then it'll be a lot easier for you to tell me where your work is. Okay, so so you'll go on to Webassign, and for practice, there's that the diagnostic test. So you can do that one and you can do your work. I'm not going to check your work. It's just to get you to try it, right? And so to get you set up before. So it's not for marks or anything. So I posted a diagnostic test on Webassign, and not for marks. So don't worry, if you don't want to do it, then that's fine. If you just want to kind of go in guns blazing on Friday, then that's fine. But I just wanted you to have a chance to test it out. So I posted a diagnostic test on Webassign. Use it to practice uploading your work to Gradescope. Okay. So what you'll do is kind of the steps. You go and you open the quiz in Webassign. So open the quiz in Webassign. Do the work. Do the work for each question on paper. On paper, or I'll say tablet if you prefer, right? If you have one. And then make sure you clearly label each question. So however you want to do that, clearly label each question. Okay. When you're finished, right? Or I guess I should say that even questions that don't require any work, you should still put your answer, right? So jot down your answer just so we have a record, because last term what happened was someone did a test and they thought they submitted it. It didn't submit for some reason. And because they sent me the work, I was able to give them marks for the questions that they were able to send me. But the ones that didn't require any work, they didn't have jotted down. So it's just kind of a safeguard in place. So just jot down the answer, even if it doesn't require any work. So even if a question does not require any work, write down the answer. Okay. When you're finished, you're going to scan your work. Now, you might have like a big scanner, that's great. Most of us don't, right? Even though I guess I do technically, I still use my phone as a scanner instead. So there are a lot of free scanning apps that you can use. And that's probably the easiest way. Otherwise, you're taking pictures and you have to organize the pictures, which you can do in Gradescope. You can upload pictures, but I do find that it's quite a bit cleaner if you're just able to upload one file. So you'll scan your work using probably a scanning app. There are a few good ones. I know, what's that one? The one that everyone, a cam scanner. Yeah, so Adobe Scan, I tried Adobe Scan, Cam Scanner, there are lots of different ones. If you're on an iPhone, Scannable is really, really good. I really like Scannable, but it's Apple only. So you'll need some sort of scanner. And part of the reason why I'm setting you up so you can kind of practice this is so that you can practice scanning and uploading. So when finished, scan your work. Oops, scan your walk, your work. Okay, so some apps, scanner apps. We had some come in here. There's Cam Scanner, Adobe Scan, and Scannable, which is for iPhone. Okay. So then, I mean, I trust that you're able to save your work and just kind of save it and send it to yourself somehow, right? And then upload your work to Gradescope. Upload your work to Gradescope. Okay. It's going to prompt you to tell me or tell it where each question is, so where the work for each question is. So when prompted, oops. Assign each question to the appropriate page. Assign each question to the appropriate page. What's nice is the order doesn't actually matter. So if you end up doing, you know, question 7 first and then question 2 or something like that, then that's fine, because you just tell it where your questions are. Okay, so you can use the diagnostic test. It has 13 questions. The diagnostic test is it's just a refresher from pre-calculus or grade 12 if that's when you last did math. Right, and so there's going to be a lot of quadratic formulas on there, right? So for the diagnostic test, recall the quadratic formula. Which says x is negative b plus minus the square root of b squared minus 4ac over 2a. Yeah, you'll use that a lot to find the roots and to find, to be able to factor a quadratic. Right? So that's just a little side note that I think you'll find helpful for that diagnostic test if it's not coming to you right away. Okay. Like I said, not for marks. Usually what I'll do is I'll just kind of use it to boost your grade later if you did it. If you didn't do it, then don't worry about it. But so it's not for marks. It's just for you to practice before the quiz. So are there any questions about the quiz? So I was kind of, I'm so torn because I think I said in the course outline, we said that the quiz would be at the beginning of the class. Now, what's hard about that is, so you do the quiz and maybe you're fast or maybe you're frazzled after or whatever, right? And then it's hard to go in and have a class afterwards. But then at the same time, I don't want to introduce new material and then have the quiz at the end. So I'm just kind of torn. So we'll have the quiz at the beginning of the class this week, and then we'll see, but let me know what you would prefer, right? I just think it can be confusing if we cover new material and then go into the quiz, and that's how we end our week. But anyways, it's an option. I'm open to either. So on Friday, we'll do I'll have the first 15 minutes of class. So from 10 to 10:15, okay, we'll just have kind of I'll be here if you have any questions before the quiz, right? Or just to make sure that you know how to upload stuff. We'll have kind of questions before the quiz, right? Maybe no huge questions before the quiz, right? But if you just have quick questions or kind of getting set up, / get organized. And then from 10:15 till 11 is when we'll do quiz number 1. Okay. And then at 11:05 is when I'll start the quick lecture after. So 11:05 till 11:50, 11:05 till 11:50. Notice there's a 5-minute gap there just to kind of, and I'll give you a little bit of time there to upload your work because it's our first day. We'll have lecture. Okay. I'll be here in Zoom the whole time, right? Especially because it's our first one. So if you have any questions, then come on by. Otherwise, you don't have to be here for the quiz. If you just want to join for the lecture after, that's totally fine. All right. All right. Any questions before we start our review? Hopefully that makes sense. It's always hard in the beginning of the term when we're trying to kind of, oh, okay, this is how we're going to do things. And I feel like I'm still trying to figure out what the best way to do stuff is too. So that doesn't help. But like I said, if you have any questions, let me know. All right. So kind of a quick review, but we finished section 1.2 last day. So we're not going to go back in there. But we did do, so for a review, right? We went through and we established just, oh yeah, so someone asked me if you need to have your camera on during the quiz. No, you don't. For quizzes, no, you're on your own, you're alone. They're worth so little that they don't matter. For tests, I might get you to have your camera on. I don't know, definitely for the final exam, I'll get you to have your camera on and I'll watch you just to make sure that you're, working alone and that kind of thing. But for quizzes, no camera. For tests, I can't decide yet. And everything is open book. Yeah. So everything's open book, but you can't work with each other, of course. As long as what you're producing is your own kind of thoughts and what you're able to gather from all your materials, then I'm happy. So open book, yes. Good. All right. And like I said, it's just going to be material from 1.1 through 1.4, or as far as we get today. Now I'm all blabbing, so we'll see. Okay, so for review, right, we established a catalog of functions. You're allowed to use Desmos, yeah. You can use Desmos for graphing, you can use it for calculator. If you don't have a handheld calculator, that's fine. It's kind of a weird term anyways, so you're allowed to whatever calculator you want. Yeah, and you are allowed to use Desmos. Good. So we established a catalog of functions. A catalog of functions, right? To help us to recognize some of these more common shapes, right? So how I want you to think about it is, if I ask you what shape is this, you'd say, well, it's not really a circle, right? But it's a circle, right? And so, and if I tell you, oh, it's a square, then you know what shape that is. The same kind of extension that I want you to have is if I say, oh, it's a quadratic, then you think, okay, it looks like a parabola, right? Oh, it's an exponential function, right? Then you say, oh, okay, it looks like this or like this, depending on the base, right? And so just like we have those kind of core shapes, right? I want you to kind of work on those functions so that if I say, oh, it's a sine function, then you know what that looks like, right? It goes through the origin and it's just kind of cyclical like this. Right? So that's what we're working towards. So we established a catalog of functions. I'll just put an end to that there. So today, we're going to keep talking about functions and mostly how do we kind of morph a function from one thing to another, right? And there are a couple of ways that we can do that. We can do transformations, which is usually graphically, right? So we can shift things up by 3 units and to the right, and we can expand it or we can shrink it. And so there's a lot of those things that we can do. I'll put this on a fresh page here. So section 1.3 is called New Functions from Old Functions. Okay. So one of the ways that we can create new functions is through transformations. One of the ways we can, and I'll say create kind of in air quotes, new functions is through transformations. Okay. I'll bring in those quick recaps right? And we'll revisit the transformations as necessary. We've got kind of more important things to do, so I'll put them in here, and we're not going to spend a ton of time on it. There is a question on that diagnostic test where you do the transformations. So it's good to have under our belts, but we'll just come back to it as we need it. Okay. So we will summarize transformations here. And revisit as needed, right, throughout the term. What I typically find is that we don't refer to it that often, so that's why I'm not going to spend too much time on it. Okay. First, I'll bring the vertical and horizontal shifts in, and then the stretching and reflecting. We can talk about them briefly, but like I said, we'll just kind of come back to these as we need them. But you will use these in that diagnostic test if you decide to do it, right? Which might be a good way to kind of get in the groove anyways. All right, so things like f of x versus just x is going to be really important when you're talking about transformations. So f of x plus c minus c shifts the whole graph up or down on the y-axis. Whereas if you're manipulating just the x, right, then at least in my mind, I find that it goes the opposite way that I would think it would. So if you do x minus c, it actually shifts the graph to the right. Whereas usually if you do x minus some amount, you would want it to go to the left, probably. So here, right? And then if you do x plus c, it actually shifts it to the left, and x minus c shifts it to the right. So that can be confusing, but if you have the summary here, then you're okay, right? If you've got some constant c, now let's make sure that c is greater than 1, otherwise it makes it weird. But if you do c times f of x, which is the whole function, then you stretch it vertically by the factor c, right? So you just kind of stretch it out. And then 1 over c, you shrink the graph, so it gets like this. Whereas if you've got the c on the x, right, so you've got some constant multiplying the x variable, then again, when you're dealing with the x, it kind of behaves the opposite of how I intuitively would think it would behave, right? So c times x actually shrinks the graph horizontally like this, and then x over c stretches it out. Okay? And a good way to check it out is to use Desmos and just kind of graph a couple of different graphs and see how they change, and just kind of convince yourself that it's in fact true, right? And then of course, if you take the negative of a function, then it reflects it about the x-axis, which you can convince yourself, right? If all the positive y's are turning negative and then the negatives are turning positive, right? Because f of x you can just read as y. Whereas if you take negative x's, again, so here, this is the only one that's kind of, it makes sense in my mind at least, then you're reflecting about the y-axis because all your positive x's are turning negative and your negative x's are turning positive. Negative of a negative makes positive, right? So that's just the kind of graph transformations, but it is one way that we can create new functions from kind of those core functions, right? that we talked about last day. Let's talk about combinations of functions. So what we can do is we can add, subtract, multiply, divide functions. And let's bring in our little blurbs here. Actually, I'll just summarize that. Okay. There. We can combine functions algebraically. For example, we can do f plus g of x, right? Assuming we have some function f of x and g of x, f plus g of x is just going to be f of x plus g of x. But of course, this is going to turn into one function. And so there we have one function, a new function from two old functions, right? Which is kind of the theme of this section, how we can morph into new functions. Same thing, right? We can subtract, we can multiply, and we can divide. I'll just list them here, but f minus g of x is just going to be f of x minus g of x. So you just take your functions and subtract the two. F g of x is f of x times g of x. And f over g of x is f of x divided by g of x. No surprise there. Okay. So we'll talk more about the domain than we did in pre-calculus, for example, because now in calculus we'll need to be really aware of the domain. And so the domain for each of these, if f has a domain of A, let's say, and G has a domain of B, right? So all the input values for f are in A. So let f of x have domain A and g of x have domain B, right? So some set A and B, right? Then the domains for all of these are going to be the intersection, right? So the overlap of A and B. The domain for all the combinations above will be A and B, right? Which is the intersection of A and B. Just as a little reminder, right, from sets, if you've got this upside down U, that's and, right? And so that's where you have the overlap, which I'll just kind of clarify there, overlap. Okay. So you'll need to find the domain of A and the domain of B and then find where they overlap. And it could be the set of real numbers, for example, which is all the numbers from negative infinity to positive infinity. The only one that has an additional restriction is here. If you do f over g of x, then f of x divided by g of x, we've got that additional condition that g of x can't be 0, right? We know we can't divide by 0, and so here we're just saying, okay, and you need to exclude all the values that make g of x equal to 0. Additionally, f of g of x, which is f of x over g of x, where g of x is not equal to 0. And I'll add that up here too. So the domain here, the domain is the set of A and B. I'll just skip the curly brackets. So as well as g of x not equal to 0. Just trying to make it more accessible. Because you've got the set notation in the notes there. Okay. So I want to hold off on examples until we do compositions, because that's going to be more important for us, especially with inverses coming up. Okay. So hopefully this kind of rings a bell, and can review it in your textbook if it doesn't, but we'll come back to it if we need it. But you just smush your functions together. Okay. More importantly, let's talk about function composition. Okay. So if you have two functions, f and g, then the composite function, which we kind of denote by fog or f, and then the circle here is called composed with g, right? So you read this as f composed with g, which is also called the composition of f and g. By definition, f composed with g, and you can kind of hear it if you say it out loud, right? F composed with g is you're going to use g of x as your input, right? So here, just kind of might make a note here. You read this as f composed with g. Oops, helps if I finish my sentence there. Okay. So what it's saying, right, is f of g of x, or actually I'll write out the whole thing. F composed with g of x is the same thing as f of g of x. One thing that I think you'll find kind of helpful is if you read this, so you might want to read this as f of g of x, because that's how you end up writing it anyways. And I find that this way is just more, it's just easier to deal with. But technically you're reading f oh, I lost my pointer here. Hello, there we go. F composed with g of x, but really if you wanted to kind of think of it as f of g of x, then it's more obvious that you're inserting g of x as the input. Oops. Use g of x as the input in f of x. Okay. Now the tricky part here is how that affects the domain, right? And so just remember that, okay, well, f has a domain and g of x has a domain, right? And so you want to make sure that the domain of g of x is satisfied, as well as the outputs of g of x have to satisfy the domain of f of x, right? Because g of x is going into f of x, and that can be a little bit tricky sometimes. I'll try to keep it kind of pretty basic, but the domain for f composed with g of x must satisfy the domain of g of x the domain of g of x, oops, because it's going in there, so it has to be defined, okay, as well as g of x must satisfy the domain of f of x. The domain of f of x. Yeah. Okay. Good. So I want to do a couple of examples here. Okay. Copy. So here we're given two functions. If f of x is x to the power of 2 and g of x is x minus 3, we're going to find the composite functions f composed with g and g composed with f. And what we'll find is that they're not the same, which should be pretty obvious, but we'll just highlight that. Okay, so first thing we're going to do here is f composed with g of x, and I usually write it out like we did here instead, f of g of x, and write f of g of x. And depending on if you want to build from the inside out or from the outside in, and I'll show you what I mean. But what you can do is use g of x as your input. So write out f of x and then replace all your x's with g of x. And then in the next step, replace g of x with x minus 3. Okay. Or if you prefer to do x minus 3 into f and then write out your f, you end up in the same spot anyways. So how I'm going to do this is say g of x to the power of 2, right? F of x is x squared, so f of g of x must be g of x squared. Now I can replace g of x with x minus 3, so x minus 3 squared. Okay. I'll make some notes here. Replace x with g of x in f of x, okay, and then substitute g of x. If that makes sense. Okay, let me see here. Good. All right. So we can expand this if we want to. I might just leave it like this until I'm ready to compare these in case I need to manipulate it somehow. So now let's find g composed with f. G composed with f of x is going to be g of f of x. You know what? I'll bump this down to its own page there. So g of f of x. So now what I'm going to do, and how I prefer to do it, is just write f of x minus 3 and then replace f of x with x squared. So I get f of x minus 3, and then f of x I can replace with x squared. So it's x squared minus 3. This looks a little bit like this, but you have to be careful, right? If we expand this out, they're going to look different. So what we can do is we can say, okay, well, this is the same as x minus 3 times x minus 3, and I can expand this out to make x squared minus 3x minus 3x plus 9, which is x squared minus 6x plus 9. Right? And so we notice that x squared, or I'll even say this, f composed with g of x is not equal to g composed with f of x, since x squared minus 6x plus 9 is not equal to x squared minus 3. Right? So that's just establishing that the order matters, how you insert functions into each other. So let's practice the domain here, right? So f of x is x squared. X squared has a domain of, I can put any value of x in here and still get an output, right? We know it's the parabola, so it helps to know the shape, and we know the domain is from negative infinity to positive infinity. Same thing here. How do you take the minus 3? Do you mean here?
Yeah.
Yeah. So here, x squared minus 3, there's nothing you can do about it. It's just going to be x squared minus 3. And then it just depends on what your x is. So let's say x is 2, right? 2 squared is 4, and then minus 3. Next one. Does that help?
Yeah, thank you.
Okay. So the domain for f of x is all real numbers. The domain for g of x is also all real numbers. You can take any number and subtract 3 and it'll still give you a number, right? And so in general, if you have a polynomial, the domain for a polynomial like this, it's a tiny polynomial, but it's still a polynomial. It's a linear function, but is going to be all real numbers. So in this case, right, all real numbers can go into all real numbers and vice versa. So there's no hiccups here. We'll do another example where we have to actually work on the domain, right? But here, just to kind of convince yourself that the domains are all real numbers for both of these. And therefore the combinations as well. So let's see here. So now we have f of x is the root of x, and g of x is the root of 2 minus x. Okay. We know square roots have the restriction on the domain that we can't take the square root of a negative number, rather. Right? So we've got conditions on x and 2 minus x here. So we need to incorporate those into our domains. Now, we're going to find each of these functions, right? And we can do compositions of itself, right? F composed with f. I can stuff f of x into f of x, and I can create yet another function, right? I can stuff g of x into g of x and create another function. So that's totally allowed. And we're going to check the domains for each of these. So let's start with A. Okay. Let's find the function first. F composed with g of x is f of g of x. Now, whether you want to do the root of 2 minus x into f, that's fine. But what I'm going to do is I'm going to write out the root of g of x. So I've got the square root of g of x here. And then in my second step, I'm going to replace g of x with the square root of 2 minus x. So now I'm taking the root of 2 minus x. The root of the root, if we just kind of flash back to exponents, right, to take the square root of 2 minus x, you would do 2 minus x to the power of 1/2. And then you've got the power of 1/2 on top of that. So this is going to be the fourth root because 2 times 2 is 4. So here you've got the fourth root of 2 minus x. Okay. So let's deal with the domains. So f of x has domain where x has to be greater than or equal to 0. Okay. And that's fine. G of x has domain 2 minus x has to be greater than or equal to 0. I can take the square root of 0, right? I just can't take anything less than 0. So here, I'll do a little bit of manipulation. I have to be careful with these inequalities. As soon as I'm multiplying or dividing by a negative, I have to switch the sign. In this case, we will do that, so we have to be careful here. But first thing, I can subtract 2 from both sides. So I've got negative x is greater than or equal to negative 2. Okay. To get rid of this negative, right, x has to be less than or equal to 2. Sign switches when we multiply or divide by a negative. Okay. So here, right, what we're saying is that x has to be greater than or equal to 0, okay, for f of x, but then x has to be less than or equal to 2. Now, it matters how we put things in. So remember, g of x, the domain for g of x has to be satisfied because it's going in there. So already we know that x has to be less than or equal to 2. Okay? But then, and if you remember the graph of the square root, right, we can't get any negative numbers from the square root, right? So it doesn't matter as long as I put x less than or equal to 2, which is going to satisfy g of x, the square root from g of x will never yield any negative numbers. So that's not a concern for us, right? You can also look at the final function. Often that will be the case, right? But not always. We might lose some things if we're canceling. Right, but the fourth root, the even root of a number, I can only take of positive numbers, so 2 minus x has to be greater than 0. So how I'll summarize this is our composition must first satisfy the domain of g of x, which is x less than or equal to 2. And then the outputs of g of x must satisfy f of x. Okay. the square root, right, will never be negative, since g of x is the root of 2 minus x, will always be positive, I guess, or 0. Any output of g of x will satisfy f of x. Any output of g of x will satisfy the domain of f of x. So therefore, the overall domain, if we want to get kind of fancy, we can use set notation, the set of all x's such that x is less than or equal to 2, or if you prefer interval notation, which is kind of common for especially Webassign, they like to have you answer in interval notation, then it's a set from negative infinity up to 2, including 2. You're allowed to put 2 in there. Okay, so kind of did that one nice and slow. Let's do the next one. So G composed with F. So now I've got the root of 2 minus f of x. 2 minus f of x, well, f of x is the root of x, so I've got the root of 2 minus the root of x. So now, oh, I guess I skipped a step. Let me just fill that in here. I'll bump this down one line here, because this is going to be g of f of x. Can't believe I skipped that. There. So first thing you need to do is make sure that f of x is satisfied. Now, how we satisfy the domain of f of x is just that x has to be greater than or equal to 0. So here, the domain of f of x is that x has to be greater than or equal to 0. Okay. And then again, because the root of x, as long as x is greater than or equal to 0, will always be positive. So, but now I've got this added condition that the root of x, so 2 minus the root of x, has to be positive as well. Okay. So, let's see here. We need f of x to satisfy the domain of g of x, which is that 2 minus x has to be greater than or equal to 0, right? Or rather, 2 minus f of x has to be greater than or equal to 0. Yeah. So if you replace f of x with the root, right, and just kind of do 2 minus the root of x has to be greater than or equal to 0. So now I've got, I can do the same thing that we did earlier, right? I can subtract 2 from both sides, so I get negative root of x is greater than or equal to 2, negative 2, sorry. And then when I get rid of this negative, then I have to switch the sign. So the root of x is less than or equal to positive 2. And now I can solve for x by taking the power of 2 to both sides. So x is less than or equal to 2 to the power of 2. So x must be less than or equal to 4. Okay. And there are a couple of ways that you could have gotten there, but as long as you landed on x has to be less than or equal to 4 to satisfy g of x, then you're good. Okay. So what we have is, well, we said x has to be greater than or equal to 0 in order to satisfy f of x. And then f of x went into g of x. So we need to make sure that that satisfies the inputs. So our overall domain is going to be the overlap of these two. So x has to be greater than 0, greater than or equal to 0, as well as less than or equal to 4. So now I'm restricted to be between 0 and 4. So the overall domain is x is greater than or equal to 0 and x is less than or equal to 4, which means that I'm restricted to the domain must be between 0 and 4. I'll use square brackets because they're inclusive. And just because it's a little bit easier to read, I'll just use interval notation. Okay, good. Let's see here. C, f composed with f. Okay, so now I'm stuffing the root of x into the root of x. So f of x. Okay. So now I'm taking the root of f of x, which is going to be the root of x, which we saw earlier, right? Very similar, but this is going to be the fourth root of x. Okay. And I had the condition on f of x that x has to be greater than or equal to 0. And I know from the roots, I'm going to be able to put any root in here because it'll always be positive, right? And so the only restriction is that f of x has to be, or x has to be greater than or equal to 0. Domain x has to be greater than or equal to 0. Okay. All square root of x are greater than or equal to 0. So the only condition is that x is greater than or equal to 0. So then our domain here in interval notation is that it has to be from 0, including 0, up to positive infinity, and then round brackets around infinity. And then finally, G composed with G, and G composed with G, whoop, catching up here. G, remember, is the root of 2 minus x. So now I'm stuffing the root of 2 minus x into the root of 2 minus x. So let's see here. G composed with G of x is G of x, which is the root of 2 minus G of x. And so, and just as we go along here, you can make note, right, that G of x has the domain that 2 minus x has to be greater than 0, greater than or equal to 0. And we actually did that work earlier, right? We said G of x has the domain that x has to be less than or equal to 2. So whether you wanted to refer back to that or just use it, that's fine. In fact, I'm just going to go x has to be less than or equal to 2. Okay. And then we need to make sure that 2 minus g of x is also satisfied. So let's see here. The root of 2 minus the root of 2 minus x. Okay. So now I need to make sure that the root of 2 minus x is greater than, or sorry, is less than or equal to 2. The root of 2 minus x is less than or equal to 2, which says that 2 minus x has to be less than or equal to 4. Negative x has to be less than or equal to 4. Sorry, I subtracted 2. So x has to be greater than or equal to negative 2. Let's just make sure that makes sense. Negative 2 and 2 is what I'm stuck between then. All right, it has to be greater than or equal to negative 2. Because if I do 2 plus, checks out, right? Because if I put in negative 2 here, then I get 2 minus negative 2, which is 4, right? Square root of 4 is 2, right? Which is the lower bound on my inputs here. Let's see if I can crank this up to the same page because it's just one line off. How about that? So then the domain here is that x can be from negative 2 to positive 2. Good. Right. Because I'm looking at the overlap between these two. So that is going to require maybe a little bit of practice to get back into the groove. I know, at least for my sections of pre-calculus, we don't focus so much on the domain, so that's the new part. The function composition is probably, you know, you're kind of used to that by now, but the domains might be the kind of new tricky part. You know? But as they come up, we'll get used to them. All right, so let's take a quick kind of 5-minute break, and then we'll do 1.4 after the break. So 11:15, let's meet back here. Break until 11:15. Back up again. Remove this. Okay, so if you had a look at the 1.4 notes, my apologies. I posted those, I think I posted them this morning or maybe last night. I don't know why I didn't post them earlier. I had them, sorry guys, I'll be better. So anyways, but it's really just a review of exponential functions, which we saw last day. So it's just kind of going deeper into exponential functions. So 1.4 is on exponential functions. One thing to note is we kind of have two similar functions, and it's just important to highlight that if you have f of x is 2 to the power of x, for example, right? This is an exponential function. Okay, so an exponential function, I'll put that here. And the reason is because the x is in the power, right? Or in the exponent. X is in the power, right? Or exponent. A power function, kind of, and maybe that's why I shouldn't say power here. I'll dump this, pretend it never happened. So x is in the exponent, whereas a power function has the shape f of x is x to the power of 2, for example, where x is in the base, right? X is in the base. And we'll kind of compare the two in example 2. But what we'll find is that when we have the variable in the power, it's going to increase much quicker, right? For large values of x, it's just going to blow up. Okay? Remember, so just some terminology, we've got the base here, which is kind of the, well, it's the base of our power. And then we've got our exponent, and what that means, let's go there, exponential functions. Oh, now it's decided to not listen to me. There we go. So just remembering that if you have a times a times a times a, n times, you can rewrite it as a to the power of n, 2 times 2 times 2 times 2. Can't remember what I said, but that would be 2 to the power of 4 maybe, if I said 4 2s, where the base is what's being multiplied and the exponent is how many times it's being multiplied, right? And so that should be kind of definitely a review. But if you have something like f of x is b to the power of x is a general exponential function, okay, and b is the base. I'll clean this up, make it look like a little bit of a cleaner b. Okay. There are a couple of things to keep in mind about kind of exponent laws. So to draw from our exponent laws, the first thing is that if you have a power of 0, okay, so assuming that the base is not 0, that's kind of a big assumption, or kind of basic assumption. But anything to the power of 0 is going to be 1. So let's summarize that here. Any base to the power of 0 is 1. Okay. And if you have a negative exponent, it's really saying, okay, well, that should be bumped down to the denominator if you were to write it as a fraction, right? And so negative exponents, I'll say bump the well, not the whole function. Sure, bump the function. I shouldn't say function, should I? The function's the whole thing. Bump the, let's say, the power to the denominator. Easier to remember than to kind of summarize in words, right? But if you use negative n as your power, then you really have 1 over a to the n. Another kind of trick we used, right, to take take the nth root of a base b by raising it to the power of 1 over n. By raising b to the power of 1 over n, right? So the nth root of b you can rewrite, and this is how you do it on your calculator, right? B to the power of 1 over n. So if you have to take the 13th root of 7, you're going to do 7. So just for example, 7 to the power of 1 over 13. Okay, so just remember that's how these exponents work. So negative exponents, bump it down to the denominator. Fractions in the exponents give you roots or radicals. So if we have b to the power of p over q, right? Then what does that look like? If we remember that we can split this up, right? B times 1 over q, or sorry, p times 1 over q. So we can rewrite this as b p over to the p over q is going to be b to the power of p times 1 over q. Okay. So remember, you can split those up, that's fine. And then that helps us manipulate things a little bit. And so what we have is we're taking the qth root of b to the power of p. So the qth root of b to the power of p, or if you prefer, depending on which order you kind of do these in, right? You could be taking the qth root of b and then raising it to the power of p, and what you'll find is that they're equivalent. So the qth root of b then to the power of p. And by exponent laws, these are equivalent. These are equivalent. Okay. So we'll summarize the laws of exponents. There's not that much that we'll need here, but I do need you to be really, really fluent in these laws, these exponent laws. So if you have a and b are your bases, then if you have b to the power of x plus y, well, usually we go from the right-hand side to the left-hand side, right? B to the power of x times b to the power of y. You can combine those, as long as you have the same base, you can combine them by adding the exponents, right? Same thing with subtracting the exponents, or rather, if you have the same base and you're dividing, right? And just to kind of emphasize the linkages here, right? If you think about b to the power of y, that's really b to the negative y, right? And then you have x plus minus y, so x minus y, right? And then this is the property that we just used here, that I can kind of move the x and the y outside as long as they're multiplying each other. So here I split up p over q to be p times 1 over q. I'm allowed to do that. And now I have two exponents that are multiplying each other, and I can manipulate them either way. If I have an exponent on the outside of a times b, then of course the exponent goes on top of a and b. This is only true for multiplication and division, right? It's not true for addition and subtraction. For addition and subtraction, you have to kind of do it by hand, so to speak. You have to expand it all out. So we summarized them last day, but let's just have them here for completeness. There are three kinds of exponential functions just in general, and any exponential function can fit into one of these categories. So there are three kinds of exponential functions. And I'll just bring them all in here. Oops. I guess I'll do them one by one. One, exponential decay, copy. A constant function, and finally growth. Yeah. Shh. She gets mad when she hears people on the street, I think. But who knows what she's actually thinking. Okay. So here, right, if the base is between 0 and 1, so not including 1, then you have decay, right? And we talked about this last day too. Here, if b is greater than 1, then you have growth. And then, of course, if you have 1 to the power of anything, 1 times 1 times 1 times 1 times 1 times 1 times 1 is just going to be a constant function. So that's kind of a boring special case, right? But here, notice that we're going from 0 to 1. And then here I'm picking up at 1, but neither of these are including 1 because at 1, you've just got this boring straight horizontal line. Okay. Constant where b is equal to 1. Okay. Just as a fact, right? All of these functions pass through 0, 1. I'll even add it on here. Okay, so all exponential functions pass through the point 0, 1. And if you think about what that means, well, okay, so when x is 0, y is 1. So if you think about anything to the power of 0 is 1, we said, right? Then it makes sense, right? I can put x equals 0, and if x is my power, then the output is going to be 1, regardless of what's happening around there, okay? So all exponential functions, pass through 0, 1. Since b to the power of 0 is 1, right, for b not equal to 0, assuming your base isn't 0, right? That makes it boring. 0 times anything is 0. So that's kind of a fun thing to remember, right? So you're always going to pass through 0, 1, and it just depends on what's going on around it that dictates the shape. We'll get into the natural exponential function, but what we'll find, especially in calculus, is the base that we're going to be using is the base e, and it has the special property of having a slope of 1, exactly 1, through 0, 1, right? And so that's what makes it so special, but we'll get to that in just a little bit. So let's just have a look here at a brief example. So use a graphing device. So of course I'm going to use Desmos. You can use whatever you want. To compare 2 to the power of x and x to the power of 2, like I said, what we'll find is that 2 to the power of x, the exponential function, is going to grow a lot faster than x to the power of 2. But here we're just confirming it. So which function grows more quickly when x is large? So 2 to the power of x versus x to the power of 2. Here we go. So I'm going to Desmos. I've got 2 to the power of x. Okay, looks good. And so remember, I'm concerned about what's happening as x is increasing. So which one is going to get larger faster versus x to the power of 2. Okay. Now, if I kind of zoom in here, oops. Can I zoom in here? So my x's are increasing here, right? As I move out in the positive x direction, right? Let's only talk about the positive x direction because we want our x's to be increasing. What happens is that at this point, right, at 4, then all of a sudden this exponential function takes off and it's growing a lot faster. And so it's not that easy to see here, but what we'll do is we'll zoom out and we'll see here. Oops. I think I spoke too soon. Oh, no, that is where it crosses over. So now that red line, which is our exponential function, is growing a lot faster as our x's increase, right? Because you don't have to move as far to the right in order to get the same value of y. So to get to 50, for example, y equals 50, our x's don't have to increase as fast. So we find that using Desmos, we find 2 to the power of x grows faster than x to the power of 2 when x is large. Okay. All right. So let's do an example and kind of an applied example, which is always nice. So for exponential functions, a lot of the time we'll use half-life. So if you've taken chemistry, biology, right, we'll talk about half-lives. And it's really just how long does it take for something to decay to half, right? Whether it be in your bloodstream or just for, in this case, strontium, I don't know, some sort of chemical thing. Leave it to chemistry. So the half-life of strontium-90, which we denote by 90SR, I guess, is 25 years. So it takes 25 years for it to reach half its mass, right? This means that half of any given quantity of strontium-90 will disintegrate in 25 years. Okay? So if we have an initial mass of 24 milligrams, we're going to want to find an expression for the mass that remains after t years. So we want to find this decay function for a general t, right? And we have all the information that we need here, even though it doesn't really feel like it, right? But what it's saying, or what we know, is that, okay, if we started with a mass of 24 milligrams, then in 25 years, we would be at 12 milligrams, right? And then another 25 years after that, we would be at half of 12, so at 6, right? And so on and so forth. And so it'll just keep decaying until there's a negligible amount, right? So we want to find an equation, or establish an equation, that models this decay behavior. So A we want to find the equation, the exponential equation that models the decay. Okay. It's going to be decay, right? Because it's decreasing. And so now, knowing that it's going to be an exponential function and there's decay, we know the general shape of this graph, right? Which could be useful if we're kind of checking to make sure things make sense. So what we know our initial mass is 24 milligrams, and the half-life is 25 years. Didn't realize they were so close to each other. 24, 25, that doesn't matter. Completely separate things. So what we have, right, this initial mass says that at time 0, I have 24 milligrams, right? So how I'm going to write this is I'm going to use an m for the mass. M of 0 is 24. Okay. Then I'll use m for the mass. You can use any letter you want. F of x is fine too, but here specifically we're talking about the mass relative to time. So usually we would use m of t. Okay. So next thing I know is that, well, at m of 25, I'm going to be at half of 24, right? So I can write that down. M of 25 is half times 24. Okay, that's 1 half-life. 1 half-life. If I go another half-life, so 25 plus 25 puts me at m of 50. Well, then if I don't simplify this because I want to be able to see the pattern, right, I'm going to do half of a half of 24. So I can just tack that on. So I get 1/2 times 1/2 times 24. Right? Notice that this is 2 half-lives. And notice that this is 2 to the power of 2. Right? Here, 1 half-life is 2 to the power of 1 in the denominator. Right? So let's do another one and see if we have that pattern figured out. And that can be tricky, right? If I'm not here walking you through it, then establishing this pattern can be really tricky. But the more of these you see, you'll start to realize, okay, well, as soon as I have a half-life problem, this is how they'll always go down, right? You just kind of look at the pattern after a few, and then you'll be able to see it. So another 25 years after that is out of 75, which is 1/2 times 1/2 times 1/2 times 24. So this is going to be 3 half-lives. Oops. And this is 2 to the power of 3. Okay. So how can we summarize? So what's the relationship between 75 and 3, right? So here, or 25 and 1, 50 and 2. Okay, so that can be the hard part. So what we want to do is 3 is the same as 75 divided by 25, right? 75 divided by 25. So in general, right, and let's just confirm here, 2 is 50 divided by 25. And 1, which is the power here, is 25 divided by 25. So in general, what we're doing here is we have t, 75 in this case, divided by 25, right? So in general, we're going to have m of t. So, or in general, if n is the number of half-lives, n is t divided by 25. Okay. So what we'll find here is kind of ... m of t in general, right, is going to be 1 over 2 to the power of t divided by 25, right? And you can just kind of try your way there, times 24. Okay. Because I'm going to rewrite this a little bit here just to show that my base is in fact negative, for example, and it is an exponential function. So I'm going to move this 24 to the other side. So this becomes 24 times 2 to the negative t over 25, right? From exponent laws, I can bring this exponent upstairs by making it negative, right? And then I can factor out this t, right? I can rewrite this as negative 1 over 25 times t, and then I can bring that t outside to emphasize that it's an exponential function. So this here becomes 24 times 2 to the negative 1 over 25, all to the power of t. So this is an exponential function with a base less than 1, right? Greater than 0, but less than 1. So decay, which is what we needed, right? We said, okay, well, we've got a decaying function here. So what we end up with should be decaying, right? And so here, because this t is in the power and it's outside, it's an exponential function. Okay, good. So we've got our general function, and that's hard to find, right? Now what we're going to do is we're going to use this function. So find the mass remaining after 40 years, correct to the nearest milligram. And so t equals 40 is what we want to use this function for. Now let's see here. Office hours. Little reminder. B, m of 40, just going from, the equation that we just established here, 24 times 2 to the negative 1 over 25 to the power of 40. Now, however you want to do this, if you want to use your any calculator is fine. I'm going to use that Desmos calculator. So for me, I find it's easier to simplify the exponents first and then take 2 to the power of it. So I have negative 1 divided by 25 times 40. That's going to be my power. Oops, negative 1 over 6. Okay, so now I have 2 to the negative 1 over 6, 2 to the power of, and I'm going to use this A and S button. You probably have one on your calculator, but it just inserts the previous answer, negative 1.6. So now I know what that is, and then I'll do a new calculation. So 24 times that previous answer. So I would be at 7.917, blah, 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 blah. To the nearest milligram would be 8 milligrams. Right? So I'll just jot that down. 24 times 2 to the negative 1.6, which is going to be roughly 7.917047465 milligrams. Hopefully I copied that out right, which is roughly 8 milligrams. Because I'm almost out of time here, we'll skip C, but you can try it on your own. C is just use Desmos, right? So graph M of t and figure out how long it's going to take to be reduced to 5 milligrams. And the answer should be about 57 years. Last thing, C, I'll say T is roughly 57 years, which you can check on your own. The exponential function, just so we have it. The natural exponential function doesn't really look like an N there. Has base E, which is roughly 2.71828, which has the special property of having a slope of exactly 1 through 0, 1. Which has the special property of having a slope exactly equal to 1 at 0, 1. And I'll leave it at that. There's a little example there, but it's just using Desmos again, so don't worry about it. All right. Just under the wire. Any questions? So I do have office hours now, so if you do have questions, I'll be here. But otherwise, I'll see you on Friday. And let me know if anything comes up about the quiz. We can be ready. But it is our first one, so we're just kind of getting it figured out.
All right. I shall see you Friday then. Ta-ta.
Friday it is. See ya.